Hey everyone in Chem 1111, welcome to lecture number 2 in Unit 2, the gas laws. And I want to start with a paint picture here to clarify two phrases which I think I mixed up last time. The first is called the general gas law. General has all the variables that can change. So P1 V1 over N1 T1 equals P2 V2 over N2 T2. And let's make an example. Suppose we had a sample of neon gas at 0.1 bar and a volume of 6 liters, and the sample contained 3 moles. And the temperature was 20 degrees Celsius, so you know you got to convert that to Kelvin, 293 Kelvin. Then we decided to increase the pressure to 0.2 bar, find the new volume, so this is condition 1, condition 2, put in 2 more moles, so now we got 5 moles in there, and also ramp up the temperature by 5 degrees to 298 Kelvin. So we want to solve for V2. Okay, we have P1, V1, N1, T1. We have P2. We want to solve for V2. So in the general gas law, what I like to do is cross multiply so I get everything on the same line. I suggest you do the same. So I get P1, V1, N2, T2 is P2, V2, N1, T1. And what am I solving for? V2. So V2 is P1 V1 N2 T2 over P2 N1 T1. Okay? And then make sure you have consistent sets of units, so your final volume will be in liters. We might as well plug it in. I put in the numbers. So 0.1 times 6 times 5 times 298 over 0.2 times 3 times 293. Okay, so 0.1 start again. 0.1 times 6 times 5 times 298 divided by 0.2 times 3 times 293, and I get 5.09 liters. Okay, so that is an example of what's called the general gas law. Now, lots of times you make changes to pressure, temperature, or volume, but not the amount of gas you have in the container. And that's called the combined gas law. So if N2 is the same as N1, it's called the combined gas law. So let's do an example of that. Okay, so P1 V1 over T1 is P2 V2 over T2. That is known as the combined gas law, and it occurs when N1 equals N2. So if I have P1 of 300 torr, tried a few different units, V1 of 6 cubic centimeters, which is the same thing, by the way, as saying 6 milliliters, right? A cubic centimeter is the same as a milliliter. T1 is 50 Kelvin. P2 is how many torr? If V2 is 8 mils and T2 is 70 Kelvin. Okay, so I cross multiply, so I got P2 is P1 V1 T2 over V2 T1. Am I isolating right there? P1 V1 T2 over V2 T1. Right, so P2 then is P1, so 300 times 6 times 70 over 8 times 50. 300 times 6 times 70 divided by 8 times 50, 315 torr. Okay, so now we know hopefully more clearly the difference between the general gas law and the combined gas law. And if I go back just to the general gas law, when you look at it, you see that all the experimental gas laws, not all of them, but most of the ones, all the ones we've talked about so far are in there. If I have constant number of moles and temperature, then I get Boyle's law, P1V1 equals N2 equals P2V2. If I have constant pressure and number of moles, then I get Charles's law, V1 over T1 is V2 over T2, right? P2 is equal to P1, N2 is equal to N1. That's what we mean by constant number of moles and constant pressure. If I have constant volume and constant number of moles, then I get Amonton's law, P1 over T1 equals P2 over T2. And Avogadro's law, V1 over N1 is V2 over N2, P1 equals P2, and T1 equals T2. So everything's bundled in this general gas law. Okay, so now let's go to the major topic today, which is mixes of gases. Often in nature, we'll have more than one kind of gas coming out of a volcano, for example, right? Or a scuba diving gear. You have mixes of gases. In scuba diving gears, you have oxygen and helium. And gas mixtures study leads to something called Dalton's law, which is that if however many gases are in there, the container, the total pressure is just the sum of the partial pressures of each gas that is in the container. So the total pressure is PA plus PB plus PC. And something that's going to help us with this is something known as the mole fraction. And a few of you may have taken this in grade 11 chem. Some of you, maybe the majority of you didn't. Anyway, mole fraction, it's not a big deal. The mole fraction of A is simply the moles of A over the total number of moles in the sample. Okay, the mole fraction of B is the moles of B over the total number of moles. The mole fraction of C is the moles of C over the total number of moles. If there were only 3 components, then you could tell me that mole fraction of A plus mole fraction of B plus mole fraction of C would have to equal 1. If there's 4 components, then all 4 of them together, the fractions would all add up to 1. Sometimes, I don't think we'll see it here, but instead of mole fraction, you sometimes see mole percent, so which is just 100 times the mole fraction. And Dalton's law, then, it can be shown that the total pressure is the partial pressure of A, which is just the mole fraction of A actually no, let's leave that. Let's leave that for a second. We'll get to that in a minute. Okay, so here I'm going to prove it here. Partial pressure, if I just have 2 containers, helium and oxygen, the partial pressure of helium is the mole fraction of helium, RT over V, right? PV equals nRT in total, right? P would then be nRT over V. So the partial pressure of helium would be the moles of helium, RT over V. The partial pressure of oxygen would be the moles of oxygen, RT over V. I don't find these pictures that helpful. If you want to use them, go ahead. So there's the total pressure is the sum of the partial pressures. Now, here's the mole fractions. Okay. It can be shown, you can go through the proof, that the mole fraction of A times the total pressure equals the partial pressure of A. So the partial pressure of B is the mole fraction of B times the total pressure. Okay, so if I have 3 components, the partial pressure of C is the mole fraction of C times the pressure total. The partial pressure of a component in a gas mixture is its mole fraction times the total pressure. So let's see how this works. Amount of gas introduced into a diving tank can be determined by weighing the tank before and after, charging the tank with gas. When you hear the word charging, it just means dumping gas, pumping gas into the tank. A diving shop placed 80 grams of oxygen, molecular oxygen, and 20 grams of helium in a 5-liter tank at 298 Kelvin. Determine the total pressure of the mixture and find the partial pressures and mole fractions of the two gases. So this is a classic example. You will need the molar mass of oxygen and helium. Okay, so let's look at it. Begin with the data involved. Everything's being put into a 5-liter tank. The temperature is staying at 298 Kelvin. You're charging the tank with 20 grams of helium and 80 grams of oxygen. So the moles of helium would be 20 grams multiplied by the molar mass. 5, really? Let's think for a second. Oxygen is 2.5. Moles is the mass over the molar mass. Oh yeah, helium is 4, right. So 20 over 4 is 5, that works. And oxygen is 80 divided by 32, which is 2.5. So that works. So the total number of moles is 7.5. The moles of helium is 5, the moles of oxygen is 2.5. Partial pressure of helium is the moles of helium times RT over V. I'm using 8.314 liters kilopascals. Okay, fine. So the kelvins cancel, the liters cancel. I get units of kilopascals, the moles cancel. So the partial pressure of helium is 2480 kilopascals. For oxygen, the only difference would be instead of 5, I'd use 2.5 moles, right? The constant is a constant. It's at the same temperature and the same volume. So 1240. So the total pressure I'd add together would be 3720. The partial pressure of helium plus the partial pressure of oxygen. Okay? Now I can get the mole fraction. The mole fraction of helium is the moles of helium over the total number of moles. So 5 out of 7.5 is 0.667. And for oxygen, 1240. Why didn't they just do the moles of oxygen over the total? They could have, right? 2.5 out of 7.5 is 0.33. They wanted to show off and show you can use moles or partial pressures, right? Because of the direct proportion. So the partial pressure of oxygen over the total pressure. So the mole fraction of oxygen is 0.333. And you see that if I add them together, the mole fractions must equal 1. So that's a good way to check that you did your due diligence. You did your work correctly, that the mole fractions have to add together to give you 1. Does the result make sense? The partial pressures are large, but diving tanks are built to withstand high pressures. To check for consistency, add the mole fractions, which must equal 1. Practice exercise 2.8. They're just changing the numbers. You can try that as an exercise by yourself. Once in a while, we talk about small amounts of gases, parts per million, which is 1 part in 1 million, ppm, and ppt is 1 part in 1 trillion, and ppb is 1 part in 1 billion. Okay. Sometimes you'll see those units. Mole fractions are all ratios of moles of a particular substance to total moles, same as with parts per million and parts per billion. So mole fraction is moles per mole, parts per million is moles per million of moles, parts per billion is moles per billion of moles, right? We said molecules, but you can multiply by Avogadro's number, so you could just as easily talk about moles. And you can say a concentration of 1 part per million is a mole fraction of 10 to the minus 6. A concentration of 1 part per billion is a mole fraction of 10 to the minus 9, right? Because it's 1 out of a billion. Okay, so we see here, oh, it says omit. There's an issue with that, so I'm not going to worry about example 2.9. Let's try a section exercise instead. But just know that sometimes you'll see part per million, part per billion. Let's try section exercise 2.31. Find the partial pressures and mole fractions of a gas mixture that contains 1 gram each of hydrogen and nitrogen. Okay, so the moles of hydrogen is 1 over 2, which is 0.5. The moles of nitrogen is 1 out of 28, right? I'm rounding a bit, that's okay. 1 divided by 28, 0.036. So the moles total is 0.536. I can get the mole fraction of hydrogen, which is 0.5 out of 0.536, which is 0.933. And the mole fraction of nitrogen is 0.036 out of 0.536, which is 0.067. And good check, right? You add those together and get 1.00, right? 0.933 plus 0.067. So that's good. I like to get the mole fractions as soon as I possibly can. So I got those. Now I want to get the partial pressures. So the partial pressure of hydrogen is the mole fraction of hydrogen, 0.933, times the total pressure, which is 2.3 bar. 0.933 times 2.3, 2.15. And the mole fraction of nitrogen is, well, we know that, 0.067. 0.067 times the total pressure, 2.3. 0.067 times 2.3, which is 0.15 bar. So the total pressure is 2.15 plus 0.15, 2.3 bar. Oh, which is what it has to be, right? So if I just go into the section exercise 2.3.1, mole fraction of hydrogen 0.933, nitrogen 0.067, partial pressure of hydrogen 2.15, partial pressure of nitrogen 0.15. It's all good. Hooray. Draw pictures, I don't care about that. 2.3.3, an atmospheric chemist. Oh, he has a good atmosphere. You know, I went to a restaurant on the moon the other day. The food wasn't bad, but the restaurant lacked atmosphere. An atmospheric chemist reported that the air in an urban area contained carbon monoxide at a concentration of 35 parts per million. So the mole fraction of carbon monoxide would be 35 by 10 to the minus 6. It's pretty small. The air temperature was 29 degrees Celsius. So I'm going to convert that to Kelvin. 29 plus 273, 302 Kelvin. And the atmospheric pressure was 745 torr. I can leave it at that, I think. What was the mole fraction of carbon monoxide? Mole fraction. Well, 35 by 10 to the minus 6 is the mole fraction. Or 3.5 by 10 to the minus 5. And then what was the partial pressure? So the partial pressure of CO is the mole fraction of CO times the total pressure. So 35 by 10 to the minus 6 times 745, or 0.026 torr, 2.6 by 10 to the minus 2, right? How many molecules were in 1,000 liters of the air? Really? They want to ask you that? Well, let's see. 1,000 liters of this air. So that's the volume. So N is PV over RT. So the carbon monoxide partial pressure is 0.026. The volume is 1,000. R, which R shall I use? I'll use 8.314. And no, I'll use 0.08314. 745 torr out of 750 point. Oh no, no, that's okay. Let's see here. Let's start again. So the partial pressure is 0.026 torr. Let's convert that into bar. So 0.026 divided by 750.1. 3.47 by 10 to the minus 5. 3.47 by 10 to the minus 5 times 1,000 over 0.08314 times, what's my temperature? 302. Times 1,000 divided by 0.08314 times 302. And then multiply that by Avogadro's number. 8 by 10 to the 20th. Yeah, I got it. How about that? 8.3 by 10 to the 20th molecules. Avogadro's number is written sometimes as an italicized N with a subscript capital A. So 8.3 by 10 to the 20th. Okay. Notice that I had to be careful with getting the value for the universal gas constant. You should probably write the universal gas constant and all those pressure conversions on an index card because you'll be using them a lot and always have that handy for you to do. Stoichiometry works for gases just like solids and liquids, but there are shortcuts. If you aren't changing temperature and pressure, then you can use the mole coefficients as if they're volume coefficients, and that sometimes helps. So let's look at this example here. We have example 210. Let me jump back to it. Okay, 2 moles of methane can, at very high temperatures, right, rearrange to give you 3 moles of hydrogen and 1 mole of ethine. Okay, so this is my chemical reaction, all gas phase. We have a 50-liter vessel filled with methane to a pressure of 10 bar at 298 Kelvin. It's heated to 1600 to convert it to ethine, and then hydrogen gas is released. What mass of ethine can be produced? What pressure does the reactor reach at 1600 Kelvin? Wow, okay. This process is a bit more than meets the eye here. So, here's our data. We start with CH4. We're charging a 50-liter tank at 298 Kelvin, and the pressure is 10 bar, and then the products are coming out at in the same tank but at a much higher temperature to make the reaction happen. So we want to get the pressure there. Stoichiometry problem, we're going to work with moles. So initially, how much methane did we have? Well, we had 1,000 kilopascals worth of it, occupying 50 liters. There's 8.314. That's the liter kilopascal per mole per Kelvin gas constant, and then a temperature of 298 Kelvin. So we start with 20.18 moles of CH4. Okay? Then how much of each product forms? Well, if I have 20.18 methane, I'm assuming you're going to completion, so I'm going to lose all 20.18. So I get half as much. So I get 10.09 of the C2H2 and 1.5 times for the H2, so 30.27. So the C2H2 is 10.09 and the H2 is 30.27. So that's how many moles of each product I have. So then the mass of the acetylene is 10.09 times the molar mass, so I get 263 grams of that. And I could also get the grams of hydrogen. I would take the 30.27 times 2. So there's 60 grams of the hydrogen. Okay, to get the final pressure, well, I know I have 40.36 moles finally. So 40.36 times gas constant times 1600 Kelvin, right, over 50. So 107 bar is the final pressure. What was the pressure at the beginning? 10 bar. Yeah, so it makes sense that the pressure would go up. I got more gas and I'm at a higher temperature. Okay. Temperature of the reactor is increased substantially and the amounts of products is twice the amounts of reactants. So a large pressure increase is to be expected in this reaction. Okay. Should we try practice exercise 210? What do you think? Sure, why not? Okay. Calculate the volume of hydrogen gas when 1.52 grams of magnesium. Well, when I see that right away, let's get the moles. So molar mass of magnesium, I think it's 24.3, isn't it? Magnesium, 24.3. Isn't that sad how I know that off by heart? 1.52 grams divided by 24.3 grams per mole. I'm sure someone's gone to America's Got Talent and just has memorized the periodic table, molar masses, and that's their job. And Howie says, oh, great job. 6.26 by 10 to the minus 2 moles. So that's the moles of magnesium. And it's reacting with excess hydrogen chloride. The gas collected at conditions of 755 torr and 22.5 degrees Celsius. And it tells me 1 mole of magnesium produces 1 mole of hydrogen. Is that true? Magnesium plus HCl goes to MgCl2 plus H2. I can put a 2 in front of there. And yeah, it's a 1-to-1 ratio. Good. So I know then that the moles of hydrogen produced is the same as the moles of magnesium consumed. So 6.26 by 10 to the minus 2. So V equals nRT over P. So I got 6.26 by 10 to the minus 2 moles of hydrogen. R, shall use the 8.314 liters kilopascals. Why not? 8.314. Temperature is 22.5. But I got to add 273 to that. 295.5. Oops. Oh, my pen got stuck. Sorry about that. Over the pressure, 755. But you divide by 750.1 because I want it in kilopascals. So it'll cancel out with the kilopascals and the R value. So 6.26, sorry, 6.26 by 10 to the second minus times 8.314 times 295.5 divided by 755 out of 750.1. 152.8 liters. Now, let's see, why does it say 1.53? Practice exercise 2.10. Let's take a look at this one. $1.53 liters. Okay, did I make a mistake here? 1.52 divided by 24.3, that's 6.255. Then times 8.314 times 295.5 divided by 755 out of 750.1. 153. I'm not using the right unit, am I? I want to convert torr to kilopascal. So if I go to the first page here in chapter 2, 1 torr. Oh, I was using bar to kilopascal. That's not good. 1 torr is 133.3 Pascal. So 755 times 133.3 out of 1,000, right? Because it's got to be kilopascal. So let's try one more time. 6.26 by 10 to the second minus times 8.314 times 295.5 divided by 0.755 times 133.3, 1.53 liters, yeah. So I did the wrong conversion there. There I was telling all you guys, oh, you should use an index card. All this, it's great stuff. Use an index card. And I didn't, and I got screwed up. Okay. Example 211 is, I'm going to omit that one. You can try that one on your own. Limiting reactants. Yeah, you try that one on your own. I'm not going to do all these questions for you. You try that one. Okay. So, summary of mole conversions. Moles are the currency of chemistry. All reactions use them. So, all three of these equations should be firmly embedded in your memory. Wow, how about that? Okay. So, if I'm talking about a pure liquid or solid, to get the moles, I take the grams over the grams per mole. Moles is grams, m over italicized m for molar mass. If I'm talking about a liquid solution, to get the moles for a liquid solution, molarity times volume. This book decides to use, most of the time, not all the time, but most of the time, a lowercase c for molarity. So molarity in moles per liter times the volume in liters gives me the moles. And then for gases, to get moles, N equals PV over RT. Okay, so yes, I would definitely put this on an index card because you have to be able to convert to moles in a whole variety of situations. Okay, and again, another limiting reactant one you can try on your own. And that will be it. So you try those questions on your own, and I see that my laptop is almost out of batteries, and I don't know where my cord is. So try them out. Ask me if you got any questions. Have fun. That's it for Lecture 2. Lecture 3, we'll look at some molecular views of gases and some other properties related to the gas laws.